We have already covered the datasheet internals, connection diagrams, and even some audio buffer math. Today, we move to the fun part, a Python script to record audio using the ESP32. After setup, I will awake the hidden Indian idol inside me. Record Sa re ga ma pa dha ni sa and play the audio. Don't worry, this is the engineering way of testing. And yes, there is more, so stay till the end. Namaste and welcome back to Avinashi Tech. The Python script itself is pretty straightforward. We begin by importing three modules: serial for capturing UART audio data, wave for creating a .wav audio file, and time to keep track of the recording duration. Next, we define some basic variables. First is the serial port. In my case, it's COM8. You will need to replace this with your own port. Also remember, this port belongs to the UART to TTL module and not the ESP32 directly. The baud rate is set to 921600. And then we define the file name where the recorded audio will be saved. In the audio configuration section, we use the same values we already discussed while configuring I2S on the ESP32. Sample rate is 16 kHz. Number of channels is 1 since this is a mono setup. The sample width is 4 bytes or 32 bits. And finally, the recording duration is set to 20 seconds. Scrolling down, inside the main block, you will see a function called record audio from serial. So let's go inside that function. We start by creating an empty list called audio frames. Then we attempt to establish a serial connection using the parameters just defined, along with a timeout. After a short delay, we enter a loop that keeps running until the elapsed time exceeds the recording duration of 20 seconds. Inside this loop, we continuously read all available data from the serial buffer and append it to the audio frames list. Once recording is complete, the serial connection is closed. Next, we open a WAV file for writing, set all the required audio parameters, and finally write the recorded audio data. The list of byte data is combined into a single byte stream using the join method and written to the WAV file. And that's the entire Python script. Simple, clean, and easy to understand. Alright, so till now we have walked through the ESP32 side firmware as well as the Python side audio script. Here, I have my ESP32 board connected to the ICS43434 I2S MEMS microphone mounted on a breadboard. We also have our USB to TTL module connected, exactly as discussed in the previous video. Great, so now it's practical time. So what we will do here is the following. First, I will either speak directly in front of the microphone or play an audio clip near it. This audio data is captured by the ICS43434 microphone and sent to the ESP32 over the I2S interface. The ESP32 then forwards this raw audio data to our Python script over a serial UART connection. The Python script receives this data and saves it as a standard .wav audio file. Now comes the interesting part. We will compare this recorded WAV file with the original speech or audio clip that we started with. I will first play a few different types of original audio recordings, and right after that we will listen to their corresponding recorded WAV outputs one by one. Let me open the PowerShell window, navigate to the script directory, and select the audio recording script. Alright, the first audio sample will be my own voice. After around 20 seconds, recording will stop. Namaste and welcome back to Avinashi Tech. This is our tutorial of I2S microphone ICS43434. Now let's open the saved file in Audacity, apply a simple effect and play it back. Namaste and welcome back to Avinashi Tech. This is our tutorial of I2S microphone ICS43434. The second audio sample will be Shri Premanandji Maharaj reciting a shlok. Once the recording stops, let's again open the file in Audacity and play it back. Now comes the interesting part. The third audio sample will be me singing Sa Re Ga Ma Pa Dha Ni Sa. Sa Re Ga Ma Pa Dha Ni Sa Ni Dha. Now let's open the saved file in Audacity, apply a simple effect and play it back. Sa Re Ga Ma Pa Dha Ni Sa Ni. The fourth sample is a kirtan by Srila Prabhupada, which includes human voice, cymbal, and mridang. Let's play this back. Now the last audio sample is purely instrumental with no human voice. Let's open the recorded file. Now let's connect the dots. The microphone recording we just heard was good enough to clearly relate back to the original audio or speech. But that won't always be the case. Sometimes you may notice a bit of noise, distortion, or jitter in the WAV file recorded by our script. One major reason for this can be sampling limitations. If the useful speech or audio energy is concentrated above 8 kHz, then a 16 kHz sampling rate is simply not sufficient to capture it accurately. Another common reason is input level mismatch. If the sound pressure level or SPL of the audio source is higher than what the microphone can handle, the digital output will clip. This clipping introduces distortion and makes the recording uncomfortable to listen to. One simple way to avoid this clipping issue is to reduce the sound pressure level at the microphone, and you can do that by increasing the distance between the audio source and the microphone. So when working with digital MEMS microphones, it's important to choose the right sampling rate and ensure the input sound level stays within the microphone's operating range. Since our future application for this microphone setup would mostly revolve around simple human speech, a 16 kHz sample rate is perfectly acceptable. If the goal was maybe music or high quality audio, then a higher sampling rate would have been mandatory for better audio detail. That would be it for this video, and I will see you again in the next one. If you found this content helpful, feel free to like, share, and subscribe to the channel. It really helps. This is Avinashi Tech, over and out.